Hello, I welcome you all to this another interesting screencast. The problem reads determine the internal normal force and shear force and the bending moment in the beam at C and D. Assume the support at B is a roller, which it is. We are able to see it. Point C is located just to the right of 8 kips load. Alright, so this problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So what we are going to do ourselves is we'll say and draw the shear force and the bending moment diagram for the beam. So find the internal forces at C. To the right of C here is important to understand the exact location because the internal force will be different to the left of this point load and to the right of this point load. Alright, here we are being asked to determine the internal forces to the right of 8 kip. Alright, so let's draw the free body diagram quickly. At A we expect AY. At B, at the same A we also expect AX. And at B we expect BY. And then the same procedure, summation of moments about point A, anti-clockwise being our reference. We have a minus moment 8 by 8, and then we have a couple moment at B, which is a 40 kips feet anti-clockwise, which is positive. And then we have BY times the lever arm, which is 8 by 3. 8 by 3 is 24, right? Equal to 0. Therefore, our BY is going to give us, grab your calculator, minus 8 by 8 plus 14 divided by 24. Oh no, we get BY equal to 1 kip. Is that so? Okay, 1 kip. Okay, so we have a clockwise moment from 8, and we have anti-clockwise, and then BY by 24. Minus 8 by 8 plus 14 divided by 24. Okay. Then let's find AY. So we'll have summation of forces in the Y equal to 0 going up in our reference. What do we have? We have AY plus BY minus 8 equal to 0. We already found what BY is. It's just here. Just replace it there. And if we place it there, we'll find what our AY is. And our AY is just going to be equal to, that's 1 minus 8. That's a 7. So 7 kip. 6 kilopound, right? Okay. What else? We have summation of forces in the x direction equal to 0. In that direction, positive. What do we have? We have just AX equal to 0, like so, 0 kip. So found all the support reaction forces. We said BY is 1 kip and AY is 7 kip, and then AX is 0 kip. Right. So let's find these internal forces. We're going to make a section just to the right of C. We say to the right of what? C. So this is the left hand side, this is the right hand side. So to the right it is here. Okay, great. So again, when you've made them section, you pick which side you feel yourself will be much easier. Okay, so for me, which side will give me a direct, let me say I'll just pick the right hand side. So let me draw the right hand side because there's it's just pretty direct, but both are direct. This is a simple problem. So we have a 1 there, keep, we have a moment, 40 keep, fit, and then this point here is D, this point here is C, right of C. Then we have shear, which will be pointing upwards like so, that's our convention, and moment like so, that's our convention, and normal force like so, that's our convention. Right, so mind you, again we are finding the normal forces, I mean the internal forces to the right of C. Okay, and this distance here is just 8 plus 8, which is 16. Great, let's go ahead. So summation of moments about point C equal to 0, and clockwise being our reference. What do we have? Okay, we have 1 keep by giving us anti-clockwise by 16. We have a 40 which is anti-clockwise, and then we have minus MC which is clockwise equal to 0. Therefore MC is just going to be equal to that's 1 by 16 is 16, then plus 14 plus 14, which gives us a 56 keep fit. Okay, 56 keep fit. All right, so let's move on to the next stage, which is finding the shear. So say summation, use black, summation of forces in the y direction equal to 0. Okay, what do we have? We have BC, okay, plus 1. Okay, what else? Equal to 0. Therefore our BC is just going to be equal to minus 1. Okay, minus 1 keep. That means the direction is in the opposite. Then summation of forces in the x equal to 0. Okay, our normal force is just going to be equal to 0 as usual. So we found the internal forces at C. Let's find the internal forces at D. So we'll make another section here at D. We are going to use the right hand side section because there is less much work. Okay, so let's draw the section quickly. Let's draw the section something like this, not something like that, it is like so. So this point here is D, this point here is B, and this is D, and here we have 1 keep, and we have a clockwise moment of, anti-clockwise moment of 40 keep fit, and at this point here we have shear of VD and moment of MD and normal force of ND, and this length is just equal to this length here is equal to 8 feet. Alright, let's start. So we have summation of moments about point D equal to 0 and clockwise being our reference. What do we have? We have a 40 positive, and then we have plus 1 feet. Okay, so we have 1 feet times 8. Okay, then plus 14, then minus MD equal to 0, and therefore our MD is just going to be equal to 1 by 8 is 8 plus 40, that's a 48. This is 40 cube feet. And then finally we have summation of forces in the Y. We have summation of forces in the Y direction equal to 0, going up being our reference. So we have VD plus 1 equal to 0, and therefore our VD is just going to be equal to minus 1 cube. And then we have summation of forces in the X direction. Okay, and we know that our ND is just going to be equal to 0 cube. Alright, we found everything else. So what we need to find now, we just want to draw again. This is not what was asked, but I just want to draw the bending moment diagram as well as the shear moment diagram. Okay, just move this a little bit there like so. Great. So let's put some lines there, some reference lines. Can I just move it a little bit again? Okay, right, so let's put some reference lines. So let's say we have shear here and we have moment here like so. Okay, so we have positive, minus, and this is the shear force diagram, and this is the bending moment diagram, and we're going to use the relationship between distributed force to shear and shear to moment. The change of moment with respect to x, dm dx, is equal to shear, and we know that the moment therefore is just equal to the area under the shear diagram. And the rate of change of shear with respect to x dv dx is equal to q, which is the distributed force, and shear itself is just the area under the load diagram. So with these two equations, we'll be able to work out or to draw this shear force diagram. Let's start with the shear force. I think I lift this a little bit up. We start with the shear force. Let's put it there. So at A, we have a boundary value of AY. So we'll have a shift upwards like so of, let's say this is a 7 kips. Okay. And then from A to C, AC, Q is equal to 0. Therefore, our dV dx, which is the slope of our shear diagram, is also going to be equal to 0. And this simply means this is the zero slope. When we reach C, there is another concentrated load, so the two are going to interact or add up algebraically. So we have a 7, then minus 8, which gives us a minus 1. So we expect the downward movement 7 kips will be reduced by minus 8, or will be reduced by 8. So if we were to draw that, then we expect this movement maybe up to there. Let's say that is our minus. Okay, so let's say this is 1. We just put 1 because we know that below is minus. We just put 1, keep. Okay. Alright, so from 1 onwards, we again know that from C to D, from C to D, from C to D, from C to D, we know that our Q again is equal to, from C to B, because this one is longer. There is nothing from C, so from C to B, our Q is equal to 0. And therefore our dV dx is also going to be equal to 0, which is the slope of our shear force diagram. So we'll have just a line with a 0 slope. When it reaches B there, we have another point load, which is a support reaction. So the two add up algebraically. We have a minus 1, then plus By, which is 1, then equal to 0. Therefore we expect a what? Closure. Business has to close. Everything that goes up must do what? Must eventually come down. Right? So we have a positive shear and a negative shear. Great. So we have done the drawing quickly. Let me wrap this stuff. Let's start the moment. For the moment, we know that from A to C, our shear force is positive and it is constant. Okay, and because of that, we expect our slope of moment dm dx to also be positive and constant. Alright, and what's the magnitude of this moment? It's just the area under the shear diagram, and it is rectangular, therefore this is just a 7 by the length, which is 8. Height 7 by 8, right? And this is equal to a 56. Okay, so we said the slope is positive and constant, so it will have a linear positive gradient. All right, the boundary at A, we know A, there is no couple that is applied at A, and it does not resist any moment, so moment there will be equal to 0. So let's draw this curve from A to C, positive and constant. So we'll have a slope. Let's exaggerate it a little bit, maybe up to there, like so. Okay, and what's this value? We said this is a 56 cube feet. Great. And then what happens from C to B? Okay, from C to B, we have V, which is negative and constant, negative value of 1, and therefore our dm dx, which will also just be equal to negative 1, is negative and going to be constant. And this magnitude is just the area under the shear diagram, which is equal to rectangular. We have a minus 1 times the length, which is 16. So this gives us a minus 16, right? Is that so? Minus 1 by 16. But we are starting from the point where we have a 36 there at C. Therefore, the two will have to first interact. So we'll have 56 minus 16. What does this give us? So 56 minus 16, it gives us a positive 40. Positive 40. So our gradient is negative and constant for moment, and the final destination is 40. So let's draw that. So from here we'll move like this up to there like this. We'll have a value of 40. So this point here is 40. This is 40 cube feet. Alright, then when we reach at B, look at this. B, we have a couple that is applied, which is counterclockwise. So if we made a section here, we'll find that just a very small section just to the left of this beam, the internal force there and the internal moment will be minus 40, or it will be clockwise. Alright, so that is the one that we're going to use in our drawing. That will add up with this positive 40 minus 40, which gives us a what? A 0. And therefore, which gives us a 0. And therefore, this is the one that closes our, it's the one that closes our diagram like so there. Okay, great. I guess we are done. And this moment here is positive. So let me clean up this stuff. So that it's ready to go. Great. And I move this stuff just a little bit. I just move this stuff just a little bit like so. I move it maybe up to somewhere there. Great. Alright, so we've done everything. We have found MC, which I'm just outlining right now. That is to the right of C. That's the moment, and it matches with what we just found. Moment there will not be to the right of C or to the left of C. Moment at C is just the same. Okay, but when it comes to shear will be different. Okay, to the right of C we have a minus 1. To the left of C we have positive 7. Okay, and then we had a D there, a D. At D we have a 48. Okay, that is somewhere mid-span. Okay, mid-span of between 56 and 50. And so if we said 56 minus 40, that's 16 divided by 2, that's 8. And then you can either say 8 plus 40 is 48, or 56 minus 8 is 48. So even that one matches. Alright, we are saying somewhere there. Okay, this is where our D is, and this is for sure a 48. Okay, and then we had finally the VD, which is the same, right? It is the same from the right of C to B. So I guess we have literally done everything. We've done everything, and I hope the video was helpful. Let me clean up this part. I hope the video was helpful, and if it was, give me a thumbs up, like my video, share my video, continue subscribing and sharing my channel. Bye bye. and see you in my next screencast.